All right. So I've got like 1, 2, 3 screens. Awesome. Okay, so I'm Norbert, and hopefully everyone has their coffee because it's 10 in the morning, and I have a lot of slides, and I should probably start my timer. There's going to be a lot of code, so if you don't see that text, you should try to get closer to the screen. What is Datalog? Has anyone heard of Datalog before? Any hands? None. You're my perfect audience because you know absolutely nothing. And this is sort of who this talk is targeted for. Who here has heard of SQL or GraphQL or Falcor? See, this is my perfect audience because Datalog, it's as old as SQL. It's like from the 70s, but it's cooler than GraphQL. So it's an amazing technology that nobody knows about, and apparently people, they don't know about it, so they don't use it in production. And from now on, you will. So we here in this room are either back-end developers or front-end developers, or maybe UX engineers or data scientists. And it turns out that we all work on the same problem. We build information systems. Information systems are these little black boxes where data comes in. We have no control over that. Users give us data. And all we can do is we can do stuff with it, right? We can store it, we can aggregate it, filter it, sort it. We can compare it to historical data that we saved in the past. Is there a lot of reverb on this microphone, or is it just me? I guess, okay, just me. And at some point, we spit that data back out, because a system that doesn't accept data or doesn't spit data back out is useless, because it's just a black box that burns electricity. And the result could be in the form of some application or UI, but it could also just be a spreadsheet or an email that you send to a user that says, listen, we've run the numbers and you need to sell all of your Bitcoin today. So what's interesting about this is that no matter where you are in the spectrum, you need to think about the information model of your domain. And it turns out that Datalog is a solution to this problem. So the idea is that you only need 3 things in order to model anything in your domain. You just need an entity, attribute, and a value. Now, I don't want you to just agree with me, right? Because the whole point of this presentation is I'm going to prove to you that you need nothing else to model anything in your domain. And that's what this talk is about. So we need a domain. So I chose GitHub because the assumption is that we all know how GitHub works, so I don't have to explain it. Fair assumption, I hope. I see nodding. So this is basically the rest of the presentation. The thing on the right is our data model. It's how we are going to store this data in our system. So you can imagine this as a file that we just append to, or it could be like a Kafka queue that we put stuff onto, or it could just be an in-memory array. The only thing that's important is that we're only going to be adding to it. We're never going to be removing anything or changing anything we already add. And it's always going to be a simple data structure with 3 elements, an entity, an attribute, and a value. And the thing on the left is going to be our code. And what I want you to keep in mind as we go along is no matter how complicated the stuff on the left gets, the right is always that simple data structure. So GitHub is users. So imagine we have some JSON payload that comes down the wire and says that there's a user, his name is Rich Hickey. So we put it into our system as 11 username Rich Hickey, right? And similarly, we're going to add Tonsky and Pitilus. So we've got 3 users. The fact that we chose 11, 22, and 33 here is completely arbitrary. Entity IDs just need to be unique and comparable. So I've decided to use integers. It could just be UIDs or anything else you'd like. And so we have some data in our system, but now we'd like to actually retrieve it. So in order to do that, we first need to talk about querying and pattern matching, because pattern matching is how we're going to build queries. So Datalog is actually a subset of Prolog. Has anyone done Prolog in the university? Perfect. So it's actually it's a declarative logic programming language that happens to be a good query language for databases, like just by accident. So the logic we're going to use here is we're going to have this 3-element vector that's going to represent the data we're looking for. So when we're talking about constants, we're just looking in this case for 11. So we're going to find any datums where 11 is the value in the entity ID. Similarly, we can find things like find the Pitilus string, or find all the username attributes, or find the datum each of those items technically is called a datum, but you can consider it an entry or anything else in the system. So in this case, we find that specific datum that matches all three values. And in this case, we find nothing, because there are 11s and there are username pithy, but not all at the same time. Does that make sense? Okay. So that's okay, but that's not very interesting, right? So in programming, we need variables. In Datalog, you use the syntax of a question mark followed by some identifier name. So in this case, E will match all entities, A will match all attributes, V will match all values. Here we're matching entities and attributes, entities and values, entities, attributes, values, right? Basically, we just did a table scan at this point. So that's not rocket science, but we can combine things. So we can say, find the constant username pithy, and then bind the entity, in this case 33, to E. Or we can look for 11 username and bind V to Rich Hickey. Or we can find all of the usernames and bind their IDs to E and their values to V. Does that make sense? Yeah. I'm going to need you guys to like nod along, because let's set up a protocol. If at any point anybody is confused, raise your hand or shout. Because the way this presentation is designed is that we're going to build these small Lego pieces and then we're going to put them into a big system. But if I lose you halfway through, then the rest of it's kind of pointless. Agreed? Cool. So a basic query, like a select where. In this case, it's called a find where. Find is what we're returning. Where is going to be just a list of clauses that tells us what to look for. So in this case, we're looking for 11 username, and we're going to bind Rich Hickey to name and return it. And notice that the return is a set of tuples. So by default, Datalog is going to return sets of tuples. So that's where you find, that's a query we're looking for a specific name, but we are actually using a logic programming language. It has no concept of order, just facts. So it's easy to flip what is known and what is unknown. So we can flip it and say, in this case, we know the username, but we don't know the ID. So it'll return the ID. Or we can say, we don't care about the ID. Find me all the username attributes and give me their names. So this will return all of the usernames in the system. Or we can just say, give me all the attributes, right? And at this point, we have one result because of sets, right? We matched 3 datums, but we returned one result. Is that all good? Perfect. So by default, we're returning sets, but we can return other interesting things. So this is the query we had previously, usernames. If there's this like weird dot notation that you can use to specify other things. So you can say, I want a list of things by using ellipses, or you can use a dot to say, I want one result. Why did it return Tonsky in this case? What? Random, precisely. It returns a set. Sets don't have predefined order. So in this case, it randomly returned one value that was true for our statement. Okay. So that's singular bindings, but now we can do multiple bindings. So we're looking for usernames, and then we're binding the E's to ID, the names to names, and we're returning a set of tuples, right? So now we know what users are in our system. So, okay, we're so far so good, right? I mean, this is pretty simple stuff. So let's complicate our model. Product owner comes by and says, users have email addresses. So how do you model that? Notice that we don't change anything we've done up to this point as far as what's in our system. But when new data comes in, we can append it to the end of our data structure, because we're using the same entity ID to say that 2 things are part of the same entity, right? So 2 attributes are part of the same entity. So in this case, we add an email for Rich and Nikita and myself. Okay, so now that we have these new facts in our system, the question is, how do we query against them? What we can do is we can do something like this. We can find the username Rich Hickey, and then we bind the entity ID. And notice what happens. When in Datalog you use the exact same identifier, it means that the constraint solver puts on a constraint that says these 2 must match, right? So what it does is it finds all the other 11s in our system. And at this point, you filter to the specific 11 that has a user email address, and you return the result. So given a username, you can return an email address. But there's no concept of order. It's just all clauses must be true. So you can flip it. You can say, if I have an email address, what is the name? Or if I give you a fake email address, then I have an empty set, because where all the clauses must be true. They're AND operation. And similarly, you can have multiple bindings. So you can say, I don't know the names or email addresses, so you give me everyone. And notice that the ID is only used as a way of joining 2 bits of information together. So is that clear? Perfect. Thank you for the people nodding along. Okay, so we complicate our model yet again. So GitHub has users, but it also has repositories. And there's a glitch. The glitch is repositories have owners, and owners are users, except when they're not. Sometimes they're organizations, right? So I want you to think about your standard SQL kind of implementation of this system, where you have a users table, an organizations table, and a repos table. And your product owner comes along and says, there's this thing called an owner on repos, but sometimes it links to one and sometimes it links to another. And usually at this point, you're kind of screwed. You start figuring out weird ways of doing polymorphism on a SQL level. So let's look at how Datalog would solve this problem. First thing we do is we introduce an organization. So we create a new entity, 44, and we give it a name, closure. Then we create a repo. So that's 55, and it's just some slug, closure. And notice it has a repo owner that's actually a value, but it's actually a reference to a different entity in our system. So I never said that values are just values, right? Values could be references to other entities. So this way you can actually create a relationship between multiple entities in the system. And similarly, we're going to create another one for DataScript, whose owner is Tonsky. Now there's a couple things I want you to pay attention on this slide. The first is it's really inconvenient to talk about these things like 44 and 22 as a developer, when you're looking at the code. So there's a nice sugar syntax, which is called a reference identifier. So basically, the idea is that there's a 2-element vector that actually maps. So it's like a query. It says find the entity such that org name is closure. So it'll find 44, and it'll replace 44 in our data structure. So we're still using the references in our data structure, but we have a nice convenient syntax that's a lot more comfortable to work with as a developer. The next thing I want you to sort of notice is that we have never introduced any such thing as a schema. We never said there are users and organizations and repos. We've just added a bunch more datums to our system. What's really interesting about this approach of modeling your domain is that you impose schemas at query time, not at runtime. Because it turns out in production, as the system grows over time, you have made terrible decisions about what your domain is. And also, your domain probably changed in the meantime. And so even if it was all true before, it's no longer true now. So you can avoid this problem entirely by writing data at such a low level that it will never change, but querying at a data that makes at a specific point in time. So I'm imposing at the application level that there are such things as users and organizations and repos only by the fact that I say that if an entity has an attribute username, it's a user. That's all I do, right, at application time. And I can change that at any moment. I can also create a form of polymorphism. If I had a business domain where an entity can act like a trait as both a user and an organization, I could just have an entity have both of those attributes assigned to it. And depending on which one I'm querying for, I'm asking for that specific behavior of that entity. And the last thing I want you to figure out is that there's a repo owner attribute on repos, but sometimes it points to an organization and sometimes it points to a user. And there's absolutely no problem with that, right? There's no reason to complicate something like this. We're simply modeling the domain as it actually exists in the real world. Is that fair enough? Awesome. So let's query that. We can do things like, let's say, find the username Tonsky, and then we map P to the identifier to 22. And notice what happens. We also use P as a value query in the next clause. So we're actually doing a join. We're saying, find me a username, Tonsky, and then find all of the repos that he owns. And after you do that, give me, find like the repo slugs so you can give me the result. So this basically says, given a username, give me all of the repos that he owns. And of course, you can flip it because it's just logic. So you can say, I know the repo, it's data script, but I don't know who the owner is, right? And I can have multiple bindings. I can say, I don't know the names or repos. Give me all of them. Now the question to the audience, why do we not see closure here? I said, give me all of the repos. Precisely, thank you. We're searching for username, not org name. We've introduced polymorphism into our domain, and now we have to deal with it, right? The truth is we're not searching for all repos. We're searching for all repos owned by users. So similarly, we can search for all repos owned by organizations. And sometimes we honestly just don't care. So we can just say or. Give me all the repos owned by users or organizations. It's very declarative, the thing we're doing. We're being very explicit about what we're requesting. Now, or is actually a sugar syntax for something that's called a rule. This is what a rule would look like. It looks like a function call. It has this little parentheses and a name. And the idea is that we can specify elsewhere in the system, we can sort of define what it means to be a repo owner. We're defining a repo owner as someone who has an org name or a username. And then we can use it like in different parts of our queries as little function calls. Now, rules have a couple of nice semantics. The first is everything that happens in a where clause must be an and, right? All clauses must be true. But the way rules work is they're all ors. So as long as one of the rules returns true, then the rule as a whole is also true. So this is a way of introducing or semantics in clauses. The next thing is that we have a name for it, so we can sort of put away a bunch of Boolean logic into one place, give it a name, and then just use it everywhere. And the third thing is that rules can actually call each other and call themselves. They're actually recursive, which is super useful because it means Datalog supports a really nice syntax and semantics for doing graph queries, where you don't know the level of traversals that you need to do. You can do things like find the minimum path between two different entities or given some certain rules, or find the maximum, or find me all of the paths. So it's really easy to do things like, let's say, given two users in the system in GitHub, tell me like how many hops, how many collaboration projects do you need to do between two of them? Like how close are they in the graph sense? So it's really easy to do things like this in Datalog. And it turns out that a lot of the kind of stuff you do in practice in production in your domain is graphs. So it's really nice when the query language supports it. Okay, so we complicate our model yet again. Repos have this concept of forks, right, on GitHub. It's a really important concept for GitHub. So how would we create it? Well, here, notice we're creating another repository, in this case, Python's data script. It's a repository just like any other repository, so it has all the attributes you would expect. But then it has an additional attribute that defines the relationship between it and some previous repo. So repo fork and some origin repo from which it came from. So notice again that we are extending our schema of knowledge without actually updating any data that we have introduced into our system so far. And notice another thing. We don't go back and give all of the repos that are not forks some kind of repo fork nil attribute. It's a really silly thing we do. It comes from the times when we were dominantly SQL-based systems, and everything must be rectangular. So if you have to introduce another column into your system that's optional, it turns out that for all of the places where it's not true, you have to start defining these things as null. And it's really silly because it turns out there's no reason for it. It actually provides a lot more semantics if you specify attributes that only make sense for certain entities. So for example, you can actually use this information to find all forks. Because if that attribute exists, I don't even care what the actual parent is. I just care that the attribute exists. I know that this must be a fork. Similarly, I can say, give me all the original repos by looking for all the repos such that that repo fork attribute actually is missing, right? And we can also talk about relationships between things. So we can, for example, define some relationship between original repos and forks. So here, we're going to look for the original repositories. Notice it finds all three, right? It finds that fork as well, because all we're doing is we're just looking for repo slug. But I'm going to give it a name. I'm going to give it a name of original ID. And then I'm going to do the exact same thing. So again, it'll match 3 datums, but I'll give it a different name, right? This time I'll call it fork ID. And it's that third clause that does all the magic, because what the third clause does is it specifies a certain relationship between that fork ID and that original ID. And when that third clause hits, the logic programming, like the constraint solver, realizes that it went too far and needs to backtrack and figure out what are the actual possible solutions to this problem. And it turns out there's only one actual answer, which is Tonsky data script maps to Pythyless data script. Does that make sense? All these simple things, and you can build complex systems. Okay, so up to this point, we were only talking about scalars. So the question is, what about multiple values? How do I store multiple values when I can only store one value because it's just an entity attribute value? Well, the simplest solution would be you store some kind of array, but that's silly because then you can't really query against it. So what do you do instead? Well, repos have this concept of languages. What languages were they written in, right? So Clojure was written in Clojure and Java. So we add 2 datums. I never said that we can't have more than one datum per entity attribute, right? If there are multiple values, let's just list them multiple times. It's just set theory at the end of the day. So similarly, data script was written in Clojure and JavaScript, and my fork was also written in Clojure and JavaScript. Okay, so now that we have that, we can do some queries against it. So we can, for example, ask GitHub, what languages do you have code in? So ignore the entities, don't care. We're actually just looking for all the repo lengths and then matching against the results. So it finds 6 datums, but returns 3 results because we're returning sets. Okay, so that's one thing. Another thing is sometimes you want relationships between things. So let's, for example, look for the repos. We use that R to bind it to the other things. We'll find the repo lengths for those specific repositories. We'll bind the languages to lang, and then we'll bind the repos to repo. And we'll get back all of the repository language combinations. So far, so good, right? It's like each step is so simple. But then we screw up somewhere, don't we? Okay, so multiple references. Most important thing in GitHub are stars. It doesn't matter how good your library is. It doesn't matter how many people use it in production. The question is, how many stars does it have on GitHub? So how do you model that? Because we talk about stars as something that belongs to repos, but it actually is modeled the exact opposite. Because it's users that star specific repositories that they like. So the way we model this is we're just going to add this concept of a user star to a user, right? So in this case, Rich Hickey liked his own repo, and Tonsky liked both Clojure and DataScript. And notice again, we're just using multiple datums because references are just like any other value. You can supply them multiple times. And I would not have that much ego to star a fork of my own, so I'm just going to star Clojure and DataScript as well. So that's how we model the domain, but the question is, how do we use it? In practice, we don't care about this. What we care about is how many stars a specific repository has, right? So what we need is an aggregation. And so this is how you would do an aggregation data log. You would take the repos. You would use the R to find all of the value repositories such that they have stars associated with them. And once you do that, you can find the people that are associated with those stars. We can aggregate that using the count P in this case. And then you can return the result. So you find out that Clojure has 3 stars and DataScript has 2. And as you can imagine, like any proper database, you have all the kinds of aggregations and statistics you would expect, right? And so this is just a case of count, but anything is possible. Okay, so except for aggregations, the other things you expect from a real production database is that you can do custom predicates, right? Because no matter how good your query language is, at some point, it doesn't support something you need. So you end up writing stored procedures. So how would this look in Datalog? So we'll find a repo, and then what happens is we'll use this funny notation of parentheses to say, call out to the host platform. In this case, we're actually using the starts with method on the string Java class, for example, right? So the Datalog implementations I'm most familiar with are Datomic, which runs on the JVM, and DataScript, which runs on JavaScript. And in both cases, it's actually funny because both of them have a string class that starts with methods, so I don't even need to change slides when I'm talking to front-end developers. But the idea isn't so much the fact that starts with method exists in Java. It's that you can use a very simple notation to call out to your host platform, which is really important because at some point you're going to have some logic that's more complicated than the kind of things you can express in Boolean logic, right? I skipped a slide, but I think it was kind of obvious, right, that we're returning closure in this case. Yeah? Okay. So there's a different example that sort of shows how this can be useful in practice. Datomic, because it runs on the JVM, has access to Lucene. So they actually give you a built-in function called fulltext, which is nothing more than a call out to the Lucene index. And so in this case, we're searching the Lucene index for closure, and we're getting back the result as well as like the relevancy scores you get from Lucene. Does that make sense? Now, the important thing isn't so much the fact that Datomic gives you a built-in Lucene function. It's that it's really easy to build custom logic when it turns out that you hit a wall that the Boolean predicate logic stuff doesn't sort of solve for you. Okay, so that was like, that actually ran a lot faster than I expected. Awesome. So we can dig into more interesting stuff. Okay, so the question, I guess, is up to this point, does it make sense? Have I sort of interested you in the fact that you really don't need anything else to model any domain? Because we've talked basically about every kind of query you'd probably expect to use in a daily life. Is someone not convinced? Why? Can you speak up a little?
Everything is good till the moment you modify something.
The perfect.
Attributes and the relations speed up.
Can I pause that question for you?
Yeah.
I'll get back to it in about 20 slides or 15. We're going to cover that topic. So aside from that, are there any other concerns? But that's a very good point. The question was about how do we do updates? So let's first talk about performance, because sometimes the obvious question is, okay, so this looks basically like a table scan. Like I've got all this data, right? It could be on a file, or it could be on a Kafka, or it's like even in memory. If I get this random query that I'm interested in, I basically need to go and look at all of these datums to figure out the ones that I'm interested in. So Datalog implementations don't actually work like that. What they do is they take this EAV structure as a source of truth, and then on top of it, they build a couple of indices that basically resolve the different kinds of queries we're interested in. So because of this really simple EAV structure, it's really easy to build all the indices you need, because it turns out that you only need this many, right? What you do is you just switch which value it comes after which, and you can emulate all of the databases that you would normally be interested in, right? So if you want to emulate a Redis, a key value storage, what you need is an AVE index, because then when you're looking at this kind of query, all of the data you're interested in is in one place, right? It's really easy to do like a O1 search for this kind of thing. Similarly, if you're looking at a SQL kind of database and you want to do a row-based query, then if you have an EAV index, again, like if you imagine this is a bunch of hash maps, then the first value and the second value gets you exactly where you need to be. If you need to do a column query, right? So this is where SQL usually falls down if you have too much data, because you're doing aggregates, and the system was not designed for aggregates. The reason why it was not designed for aggregates is because you need attribute entity value indices. Because if you have one of these sorted, then all of the user stars are in one place. So it's really easy to do a count on them. If you have a document database, if you want to emulate Mongo, you're actually using the same thing you were using it as for row-based. It's just there's a trick. So the trick is you're looking for 11 user stars, which gives you R, which gives you 55 in this case. And where most databases fall down is how do you keep going? But because here the structure is so simple, all you have to do is you have to jump down to 55 and then go to repo slug and get the answer. So the problems you usually have in Mongo or Elasticsearch or stuff like that is figuring out how much stuff you put in a single document so it's easily traversable, and how much stuff you put in separate documents that you need to jump around. Here you sort of avoid the problem by saying that this EAV structure is so simple that there's no reason to decompose into smaller things. So it's really easy to jump around and emulate a document database. But the more interesting question is, what about a graph database? A graph database actually is a query that does things in reverse. It starts with a question. It starts with the answer and tries to figure out what was the original question you were asking. So you need an index that actually reverses the values. So you actually index by value, then by attribute, and then by entity. So what happens here is we start with the final result, which is closure. So we find closure. We find the repo slug, and we find 55. And then 55 is this R. So 55, user stars, and we get back E, which is these three values. So if you have an index that's built by VAE, you can actually do graph traversals just as easily as you can do any other kinds of traversals. So the point is that using these very simple indices, you can emulate all the kinds of databases you would expect. And as I've shown previously, if you need something like full text search, then you need an inverted index, right? Like full text index, like Lucene. But as I've shown, it's really easy to integrate that into your existing systems and existing queries. Okay, so that was about performance. The next interesting thing is attributes. So this is what we've been working with all day, right? This 11 username Rich Hickey. This should be pretty familiar by now. But the question is username a string? Because it could be, but it also could not be. Because imagine if it wasn't. Imagine if it was an actual entity that we stored previously in the same system. We'll call it dbident, just as a convention. If we have this as a full-blown entity in our system, we can actually add metadata to it. So we can do things like we can say that it must be a type string. Like if you give me something that's not a string, just throw an error. You can give it documentation. You can give it hints, like I need this to be a uniqueness constraint, so when you're committing this transaction, make sure it is. You can even give it hints like, I'm going to be doing full text searches on this, so make sure a Lucene index is built for this specific attribute. It's really nice how well this stuff decomplects. So that's basically reified attributes. And now we get to the question that was asked, which is how do you do updates? How do you do transactions? So the question, as it was stated, was how do you do an update? How would you update the username to a different name? Are there any ideas? Delete the row and create new. Yes, except we just stated we don't delete data. So it's a good first try, but unfortunately it fails the constraints we applied. And also remember, we can't just add a new row because then we're creating two names for an entity. We're actually modeling the fact that you can have aliases at that point, right? There can be multiple names associated with an entity. So the reason why this is not an easy question is because it's a trick question. EAV gives you all of the tools you need to model any information in your system at rest. At rest is the key here. Changes is actually a communication of is a way of communicating change. The updates are a way of communicating change. They're not information at rest. So so this is enough if you want to model any specific point in time. But if you want to model the actual change over time, we actually need to add 2 more columns, which is why this didn't work up to this point. We're adding 2 columns. The first is transaction, the second is operation. So what a transaction is just some identifier where if there are multiple things, multiple datums that have the same transaction, it means that they happen atomically, right? And the operation is a Boolean flag that says, did I learn about something or have I forgotten about something? So if I want to add a new user into our system, I would just add a new user, 99 username, okay, at a new point in time, transaction 3000, and it's true because I've learned about this. If I ask the system before time 3000, he knows nothing about this person, but after this point, he does. Similarly, if I want to remove something, I'm adding a new transaction that says that as of time 3000, you no longer know about Tonsky. Doesn't change the fact that I knew about him before. It just changes the fact that from this point moving forward, you are no longer part of our domain. And an update is nothing more than a single transaction that introduces a retraction and an assertion. You are to forget about Tonsky, and from now on, he is known as Nikita. Does that answer your question about updates? Okay, perfect. So, those are updates. And what's interesting about transactions is, just like attributes, they can also be entities, which is really nice, because what you can do is you can add metadata. So you can, for example, figure out, like the server can say, I've committed transaction 2000 at time X. Give me a timestamp so I know exactly when this happened. And actually, we do more than that. We do things like we give them additional metadata, like who did this change, right? Who exactly changed this? And maybe also, why did he change this? If you're debugging a problem, why is a certain piece of data the way it is? And the reason for that is 3 months ago, you did an import of a bunch of JSON, and there was a problem with the backup. With this amount of metadata, you can figure out and track down exactly when this change happened and why did it happen, right? Okay. Yeah.
These IDs you are raising here, once you use them in transaction column, one in the entity. So this must be a one single line of IDs, or how should I approach it with the duplicate values?
So the question is, they're usually they're in the same range of IDs, as in, like, let's say they're all the same 64-bit integer. But what usually happens in implementations is you'll create ranges. So you'll say, like, I'm going to take a 64-bit number and I'll give 1/3 of the range for entities and 2/3 of the range for transactions. But that's usually just a implementation detail. Theoretically, you could just do it atomically, one by one, right? But in practice, usually what happens is you give a separate range for transactions and for entities. Usually there's more transactions than there are entities. But that's a good question, thank you. Okay, so do we move on? Awesome. We're actually running faster than I expected, which probably means I was talking too fast, so I apologize for that. Okay, so we can look at some stuff that happens, that sort of Datomic gives us for free as APIs to sort of think about the kinds of problems we could actually be solving if we use this approach. So one of them is an API called as-of. And so what happens is, as-of is a time-traveling debugger that says, run a specific query, but go back in time as if the last database that you saw was time 3000, right? Ignore anything that happened after that. So because of the fact that we have metadata, we can use a 3000 as an ID, or we can actually just say, find the transaction as of time, a specific date, as of last month, and then basically run this query as if I had run it last month, and what kind of data would I get back, right? So if you imagine our nice queue of datums, right? What's happening is we're just saying ignore the last bottom portion of the data and run the query as if it was just this part. So it's really easy to imagine how this actually is implemented, right? And then since does the exact opposite. It actually says ignore all of the data from the beginning of time to n and only use the datums that came after and do a query on those only. History is something that just is a fire hose of data. It's just give me all of the assertions and retractions as they happen over time. This is used, for example, mostly for auditing, right? When you want to find out about everything that happened in the system from the beginning in time. Filtering is a way of creating a read-only snapshot of the data with certain data removed. So a really common use case for this is if you need to allow querying from the client side, which is really popular nowadays because you have like these GraphQL clients, right? That basically they send a payload of this is all the data I'm interested in just run it against the database and give me the result. And because the queries are created dynamically, we don't really have control over what data the client is asking for. So either you can do a bunch of whitelisting and blacklisting and trying to figure out how to parse this query into something the user can actually is authorized to look at, or you can do something like filtering. The way filtering works is it creates a persistent immutable data structure snapshot of the data that we're interested in. In this case, we're just removing all the passwords from the database. And any query that user will run with that version of the database will actually just not have the data he's not authorized to look at. So you actually don't need to do any kind of whitelisting or blacklisting and parsing of queries from the client side. You give them, from their perspective, a complete database they can do whatever they want with. With is the exact opposite. It's actually creating hypothetical databases. It's like if you imagine that stack of datums, imagine that we added a certain number of facts to the end of it and run the query as if those facts were part of the database, right? So it's like doing a transaction query and rollback without actually touching the database, without any kind of locking or anything like that. So it's a way of doing hypothetical queries. Components. So components, I don't really want to dig into the code here. I just wanted to give this idea of sometimes there's a parent-child relationship such that the child cannot exist outside of the parent. So in the GitHub example, those are commits. Because commits have unique identifiers, the SHAs, right? But on the other hand, commits cannot exist outside of the repository. It makes no sense for them to exist outside of the repository. So what you can do is you can create this kind of parent-child relationship. In this case, we're talking about this attribute 66 git commits 110, where 110 is the data of the commit. And just the way I showed you that you can add metadata to the attribute, we could specify that git commits is actually a component. And when we do that, the database will know that this is a parent-child relationship, so it can take a bunch of hints. For example, if we delete the repo, it'll go ahead and delete all the commits, right? Like a cascading delete. If you're storing this data somewhere in the cloud, it'll know to store the commits really close to the repo because it's very likely that when you query for one, you're going to want the rest of the data as well. So it's best if it's like in the same block, right? And you can do a bunch of interesting things once you kind of give this database a bunch of hints like this. So this is not a bunch of useful code. We're just adding a couple of commits because I want to talk about the PoolAPI. So this, in my opinion, so this is like an extension of Datalog. This isn't Datalog per se, but the Datomic team that took Datalog and actually built a sensible database out of it introduced this idea of a PoolAPI, and basically it replaces GraphQL. It replaces the need for GraphQL. So the idea is we're going to take an identifier, so that's E. So in this case, we're going to find the repo closure. And we want to pull out a bunch of interesting data out of the repository. But instead of specifying all of those attributes as separate clauses that we sort of need to join together in Boolean logic, we're actually going to pass in a data structure, and that's the query. And so this is what like a data structure could look like. And so if you have worked any time with GraphQL or Falcor, the main key selling point is that the client specifies the structure of the data it expects to get back. So it specifies exactly what attributes it's interested in, and it specifies, and the shape of the data that gets sent as a query is the shape of the data that gets returned. So you don't have to, you can avoid a bunch of boilerplate between trying to parse what the backend returns and what the client needs. So in PoolAPI syntax, you use a vector as attributes. So in this case, we're interested in the repo slug, so you get back the slug. And you're interested in the languages, so it's smart enough to figure out there's multiple values, so it'll return a vector. And then you can use this curly brace syntax to say that I want to do a join, just like you would do it in GraphQL, right? So we actually join onto the owner of that specific repository. And once we're in that scope, we can again start returning attributes. So there is no username, but there is an org name, so I'll just return that one. And then we'll do another join, just to mess with you guys. Notice this time we're using _owner. So PoolAPI has this concept of reverse graph traversals using this underscore syntax. So what that means is, in the scope of an organization, I want you to find all of the repositories this organization owns. So you get back a vector of repos. And in that vector of repos, again, you can specify attributes. In this case, I'm going to make it more interesting by adding a limit. And again, I'll do another join with commits, and then I'll return a bunch of SHAs. Now, obviously, this example is a little bit of everything. The point is just sort of like to whet your appetite, that there's a really solid grammar behind the PoolAPI, and I highly encourage you to check it out. It's just like a single page of documentation of how the grammar works, and use it as a way of communicating between multiple clients and servers. In my opinion, the syntax for it is just better than GraphQL. Okay, so we have literally a couple minutes left. So what I want you to, so we've done a bunch of theoretical stuff. I wanted to leave you with some practical advice. So how can I use this stuff in practice? So the first thing that, in my opinion, comes up a lot is event sourcing, right? This is a really popular thing nowadays. What is the main problem with event sourcing? Ideas. Anybody do event sourcing in production? What's your main problem? The main problem is that you use event sourcing. So one of the big problems with event sourcing is how do you store the raw data that comes into the system? Because if you get that wrong, then you need to go and migrate data. And sometimes it's impossible to figure out how exactly data should be migrated. And even if you can figure it out, you're basically constantly changing the schema, right? We're back to that problem of we're not smart enough to figure out what the domain is, because even if we're perfect, the domain changes over time. So anything that was true now is probably not true any longer. In my opinion, the EAVT op, the 5-tuple structure, is ideal candidate as the raw data storage mechanism for event sourcing. Even if you use none of Datalog, if you store and think about attributes in such a low level, then you're never going to have to go back and try to rewrite your schema, because there is no schema outside of the fact that there's a username and it's a string, right? I mean, if at some point users don't exist, it doesn't matter. Like that event, just ignore it from now on. Okay, so event sourcing is one. Datomic is another. As in, if you want to just go and use Datalog from now on in the back end, then I highly encourage you to check out Datomic. We don't really have time to get into details, but the really short version is that Datomic splits into 3 transactors, 3 different things. A transactor that handles the writes and makes sure that there's order in the system. A storage mechanism that's actually, they don't do storage. They tell you to go use Postgres or React or Dynamo or Cassandra, whatever you want, right? Like that's a solved problem. We're not going to reinvent that wheel. And the last one is peers. And peers is basically how do you scale reads. The more peers you have, the more you can scale how the reads work. And then there's a bunch of caching mechanisms. In practice, Datomic looks more like this, where there's like mem caching and high availability and all this other kind of stuff. This is actually an architecture for Datomic on-premise. Recently, Datomic released a version that's on cloud, where they use explicitly DynamoDB, and they have like multi-master writes and stuff, and you would expect and it just runs on AWS, right? Like it's an AWS specific solution. We also use DataScript on the front end. So DataScript is an implementation of everything you just saw, but it runs in JavaScript, and it's designed to run in long-term sessions like you would have in a single-page apps. Then we use the PoolAPI as a way of communicating between multiple clients and servers, right? We use that. We use that instead of GraphQL or REST APIs. And it turns out we also use the PoolAPI as a way of building front ends where the React components themselves return snippets of PoolAPI syntax that gets sent up to the root, built into one composable root piece that can be sent to the server, or it can be queried against a local DataScript engine, right? So you use that as well. This is the last slide, basically. I have a link to this gist. It just includes some more material where you can, if you're interested in learning more about how to actually do this stuff, then check it out. It also includes a version to a deck that I made for basically like a 2-hour workshop on Datalog. It's like a much longer version of this. It goes into a lot more details about certain things that I just did not have the time to talk about today. And if you have any questions, I don't know how we're over time. We'll take a couple questions, but we can also talk afterwards. So find me in the hallway. Thank you.